In this lesson, we're start to look at force and end up deriving what are called Newton's laws, which are three rules to describe force and how force acts on an object. So the first thing we need to do is define what is a force to begin with and talk about some ways we describe forces. Generally speaking, anytime you have a push or a pull in an object, something that either causes motion or resists motion or would cause motion if something else wasn't pushing or pulling on it, that would be a force. There are kind of two main classifications if we want to talk about forces in general. One would be what we call contact forces. A contact force results from two objects being in physical contact with one another. For example, if I push on a cart, my push on the cart is a contact force. I'm physically in contact with the cart, and that force requires that I be in contact with the cart. Not all forces require there to be physical contact, and the second type of force is what I would call action at a distance, or a non-contact force. A great example of this type of force is gravity. If I drop a ball out of a window of a building, that ball falls to the ground. The reason why that ball falls to the ground is gravity pulls it toward the ground. The ball's not in physical contact with the earth, but it still gets pulled down by the earth. So this is a force that doesn't require there to be physical contact for the force to exist. Or vectors. What this means is the direction that the push or pull is acting on an object makes a difference in what's going to happen to that object, whether an object is going to remain at rest or whether or not its motion is going to change in some way. One other way that we begin to describe forces is what we call fundamental forces. And ultimately, all forces that we can think of can be put into one of these three categories. Two of these are pretty specific, and one is a very broad general category. The first one that's pretty specific is the gravitational force. The gravitational force, or gravity, is what holds us to the Earth. It's what holds the moon in orbit around the Earth. It's what holds the Earth in orbit around the sun. It's in some ways the most obvious of the types of forces that exist, and really it's one of the first forces that we begin to really describe. Oddly enough, of the three fundamental forces, it's actually the one that we know the least about right now. We don't really know how gravity works or why gravity works. We just know gravity exists. We have some models to begin to describe it. We don't really have a good understanding of what really causes gravity to exist. Where the other two types of fundamental forces, we do have some pretty good understandings of why they exist. The second one is what we call the strong nuclear force. This is the force that holds protons and neutrons together in an atom. If we think about the center of an atom, you have protons that are all really close together. You maybe remember that protons are positively charged, and if you put two positively charged things close together, they repel one another. Well, they stick together in an atom, and it's this force that is responsible for them sticking together. The third one is kind of a catch-all category for a lot of different types of forces that all end up being kind of all related to one another in one way, shape, or form. And this is what we call electroweak. And electroweak is any type of electrical interaction or magnetic interaction. Pretty much any contact force you can think of probably fits in this category because it probably involves electrical interaction between individual particles of a substance. This type of force is also responsible for lots of different types of radioactive decay, particularly those types of radioactive decay that involve charged particles. So ultimately, any force you can think of fits into one of these three types of categories in some way, shape, or form. What are some ways we describe how force acts on an object, or ways we begin to conceptualize what's happening with force? And one of the main tools we use is what we call a free body diagram. And what a free body diagram does is it provides a representation of what forces act on an object and how they're acting on an object. This really is one of the main techniques that I use to help me develop a solution to problems that involve forces. So if I know this block is sitting at rest on this ramp, I can begin to find solutions for what are some possible forces or what are the magnitudes of the possible forces based upon this orientation of this block sitting on this ramp. So when I consider an object like this or a system like this, I want to ask myself, what are forces that act on this object? What direction do those forces have to act? And how can we represent those forces? So if we think about the block sitting on a ramp, probably gravity's acting on it because it's here on Earth. If it's not sliding down the ramp, there's probably a force that prevents it from sliding down the ramp. That would be friction in this case. And there's probably a third force. It's sitting on the ramp. The ramp is probably supporting some of its weight. We call that a normal force. So when I start to draw a free body diagram, I usually start with a dot or sometimes a box to represent the object, and I then draw arrows to represent the different forces and what direction they go. I know gravity, or the weight of the object, has to push downward. It's worth pointing out that weight and the force due to gravity are the same thing. We have friction. The way I describe friction is a force that resists motion or resists impending motion. If this thing is sitting at rest on a ramp, if friction doesn't exist, this thing is going to slide down the ramp. Since we know it doesn't slide down the ramp, there must be a force of friction that acts in the direction up the ramp, opposite the direction motion would be if it didn't exist. And the last force I said was this normal force. And the normal force is really a force that is due to an object sitting on a surface. The normal force is always perpendicular to the surface an object is sitting on. You can think of it as how this ramp supports the weight of the block, or how much of the weight of the block is supported by the ramp. So here I've drawn the three arrows to describe the three forces that act on this object and what direction those forces act on the object. Some common types of forces that are in free body diagrams. One of the most common is weight, or the force due to gravity. When you're close to the surface of the Earth, weight is actually something that's really easy to calculate. You take the mass of an object in kilograms and you multiply by the acceleration of gravity on the Earth's surface, 9.8, what we call g. And so you can get the weight of an object from that measurement. The second one we use is normal force. And normal force is a contact force that results from sitting on a surface. It is always perpendicular to the surface the object is sitting on. The next one we had in my previous one is friction, which is a force that resists motion or resists what we call impending motion. The fourth one is tension, which is a pulling force that's caused by a rope, a chain, a cable, a cord, whatever you have. It's worth pointing out that tension is always a pulling force because you can only pull things with ropes, chains, cables, cords, etc. And the last one is just a general contact force, which is any force associated with the contact of the object. So if I was pushing on this block on the ramp, I might use that as a contact force. Now we'll practice some free body diagrams in class and practice some techniques to decide what types of forces might act on an object and what types of forces may not act on an object. There are other types of forces that might exist on certain objects, and you don't need to have all of these forces in a free body diagram. The one that I will say is in the vast majority of free body diagrams we do is weight. So the last thing I want to do is develop, or at least come up with, what we call Newton's laws and describe what they're actually kind of saying. Newton's laws are developed by a guy by the name of Isaac Newton. Isaac Newton lived in the 1600s. He developed these laws in the late 1600s. Newton is generally viewed as the father of kind of modern classical physics because of these laws that he started to develop and the various laws and rules of motion that come out of this set of laws. He is also generally viewed as the father or creator of derivative calculus. So if you're taking calculus now or have taken calculus, he's responsible for about half of what you would do in calculus, or at least responsible for the underlying principle that guides half of what you do in calculus. He is also responsible for what we would call optics, how lenses and prisms and mirrors work. He's kind of one of the people responsible for a modern view of how lenses and mirrors work. He's also interested in a lot of other things. He's actually a knight. He was in charge of the Royal Mint for, well, a large period of time. The Royal Mint is the institution that makes money in England. And one of the things that he was very good at is preventing counterfeiting. He was also president of a group of people called the Royal Society, which is a bunch of philosophers and scientists in the late 1600s, early 1700s, that basically is a who's who of anybody in philosophy or science in England at the time. think of putting the greatest minds in your country all together in the same club. Well, that's the Royal Society. Isaac Newton was one of the main members of this group during his time period there. The other interesting thing about Isaac Newton is if he had followed what his mom wanted him to do, he would have taken over the family farm. Instead, he went to school, he got interested in mathematics, he got interested in science, and went to college, went to university, got a degree at a very young age, and ended up basically redefining how we look at motion. So what are Newton's laws? And the three laws that we generally call Newton's laws are these three here. The first one is that an object that's in a constant, or an object will stay in a constant state of motion unless it's acted on by some net external force. So what this law says is if an object is in motion, it's going to remain in that same state of motion unless some net external force acts on it to change its motion. This is what I would generally call the law of equilibrium. It says that if there is no net external force acting on an object's motion remains constant. So this means that force doesn't necessarily cause motion. What force does is it changes motion. Now it's worth pointing out here we talk about net external force. What that means is if you add up all the forces acting on an object and you get zero, then the first law applies. The first law doesn't mean there's no force acting on an object. It just means all the forces act in a way that they add up to be zero. The second law is really very similar to the first law. And the second law says that if there is a net external force, an object experiences acceleration. Its state of motion changes. So the first law and the second law are really saying the same thing, just looking at it from a different perspective. One is saying if the net external force is zero, what's going on? The other one is saying if the net external force is not zero, what happens? This is F equals ma, what we generally think of as Newton's law of motion. The third law is probably one of the hardest ones to describe, and it really says if object 1 is applying a force to object 2, object 2 is also applying force to object 1 that is equal in magnitude and opposite direction. This is sometimes referred to as equal and opposite reaction action, or if there's an action, there's an equal and opposite reaction. I don't like the action-reaction because it suggests that force 2 happens in response to force 1, and that's not the case. These two forces happen at the same time, not in response to one another. So it's kind of hard to get that in your head that if object 1 puts an force in object 2 puts another force back in object 1, that those are happening at the same time and that they're not happening in response to one another. I usually describe the third law as that force always comes in pairs. So if you have a force acting on one object, that object is putting a force on something else. So that's kind of a quick introduction to Newton's laws. What we'll start to look at in the next lesson is how we begin to describe or use these laws to start to solve some problems.